Good morning. Before starting, I want to acknowledge the hard work and contributions of Drs. Kendra Lawrence and Janet Lensing. By altering average temperature and rainfall, global climate change will alter rates and quality of detrital input and microbial growth, potentially affecting survival and reproduction rates of many litter-dwelling arthropods. Climate change will therefore have impacts upon the detritus-based arthropod community of the leaf litter horizon. We investigated potential impacts in 2 experiments conducted in the same forest in different years. In study 1, we increased the resource base directly by adding artificial detritus. In study 2, we simulated extremes of rainfall predicted by climate change models. Both perturbations were conducted during the growing season each year. To sample larger, more mobile arthropods, we sifted litter in the field. Smaller arthropods were extracted from litter in a modified Kempson apparatus. We sampled the community once in summer and once in fall each year, for each of 3 years. Study 2 had an additional fall sample. Kendra Lawrence conducted study 1, which was based upon a previous experiment of Ben Rong Chen in the same forest. Ben had selected 20 open plots, each 2 by 5 meters, and in order to promote fungal growth, every 2 weeks for 3.5 months, Ben added a mixture of chopped mushrooms, potatoes, and fruit fly culture medium. The total amount added equaled the weight of dry leaves falling to the ground each year. After 6 weeks, collembola densities had doubled compared with control plots and were 2 to 5 times higher by fall. Generalist predators, which showed a delayed response, were 2 times more abundant in the resource enhancement treatment by autumn. This pattern was evidence for strong bottom-up control. However, the experiment ended after 1 field season. Were these increases a prediction of a new community equilibrium, one existing consistent bottom-up control for all groups that responded? Kendra Lawrence addressed this question by using smaller plots, 2 by 2 meter, but she fenced half of them to reveal if migration would influence results. During the first year, she added the same mixture as Ben did, but at only 30% of his rate. In years 2 and 3, she increased the rate 4-fold. After 3 years, the total amount of dead leaves and other detritus in the subsidized plots was only 10% higher than in the controls. The resource subsidy produced a 3-fold increase in fungal hyphae as measured by ergosterol content. Our response variables were 18 combinations of taxa and sampling method. The most abundant animals were 6 families of collembola. All our analyses focused on the interaction between resource treatment and year because we hypothesized that responses of some taxa would change as the detrital supplementation continued. How did the entire community respond to increased detrital input? First, we determined how resource addition altered the distance between communities in ordination space defined by Gower's similarity measure. We analyzed patterns separately for each season because the interaction between season and the resource by year interaction was statistically significant. There was no interaction with fencing. Communities in the ambient and supplemented treatments clearly diverged over time, with divergence slightly more pronounced in the fall, likely because of longer exposure to resource addition each year. Next, we used linear mixed effects models to analyze the response variables most closely associated with the divergence in ordination space. And today I'll present patterns for the taxa also sampled by Ben Chen. Entomobryid collembola and the 3 fall samples were 2 to 3 times more abundant in supplemented plots in all years. This graph shows open and fenced plots pooled. This will be the case in all but one future graph because the interaction with fencing was usually not significant. Hypogastrurids also responded positively, but with a clear delay. Many taxa, however, exhibited patterns different from simple, consistent bottom-up control. For example, summer spinthurid populations responded strongly, but only in the second year. Fall populations of spinthurids showed a similar pattern, as did Isotomidae and Onychuridae. Here are two examples, clearly opposite to bottom-up control. Two Collembola families in summer samples exhibited a negative response to resource supplementation with a delay of 1 or 2 years. Predators also displayed mixed responses. Cursorial spiders exhibited consistent bottom-up control, and in contrast, summer densities of pseudoscorpions were lower, not higher, in supplemented plots the final 2 years. And in year 1, web-spinning spiders were twice as abundant in the supplemented treatment, but evidence of bottom-up limitation disappeared by year 3. Study 2 was conducted with 2.5 by 5.5 meter plots that were permanently fenced and covered with a transparent roof during the growing season. Rainfall was collected, stored, and distributed to low and high treatments via a sprinkler system. Before we manipulated rainfall, we sampled arthropods in the fall and the following summer, year 0 in the graphs. Thus, the treatment times year interaction measures divergence from initial conditions. Study 2 was replicated twice at 2 sites. Site 1 was better drained and had drier, lower soil horizons. This is a distribution of rainfall during the growing season in our forest over the previous century. Rainfall manipulations reflected the predictions of global climate change models for deciduous forests of North America and were close to the extremes seen by this forest during the previous 100 years. In this study, we also measured litter ergosterol. Fungal hyphae increased about 50% each year, but never differed between low and high rainfall treatments. Out of 55 response variables, combinations of taxa and sampling method, Kempson-extracted mites were by far the most abundant group. Mites showed a clear response to rainfall by the first year. Among the remaining taxa, Collembola were numerically dominant, as in Study 1, and in Study 1, mites were not counted. The response variables were first analyzed using a multivariate approach. Interaction terms with both site and season were not significant, so communities are coded here simply by rainfall treatment. Communities in the low and high rainfall treatments clearly diverged over time. Communities in summer and fall were distinctly different, but the effect of rainfall did not differ by season nor by site for the multivariate analyses. Compared to Study 1, fewer taxa showed a response to the experimental treatment when analyzed with linear mixed effects models, but all responses were similar to those shown by mites, higher in the high rainfall treatment. Thomicerid Collembola extracted by the Kempson displayed one of the strongest responses to rainfall. The first 2 points are initial conditions for the fall and the following summer. A clear response appeared only after a year of rainfall manipulation. We also modeled the univariate patterns without the additional fall sample in order to test for an interaction with season, and results were usually very similar in both analyses. A few univariate responses varied by site, with the response sometimes being stronger in Site 1, the drier site. This was true for Thomicerids from Kempson samples. Thomicerids sampled by sifting litter also showed a strong response to rainfall, but there was no interaction with site. Among generalist predators, cursorial spiders in the sifting samples showed the strongest response. a twofold difference in density between low and high rainfall treatments. Before summarizing the results, I'd like to review the experimental designs. Ben Chen's experiment had large plots and the most replicates, but lasted only one field season. Study 1 had smaller plots and had 5 replicates, but 10 when there was no interaction with fencing. In Study 2, plots were almost 3 times as large as in Study 1, but the degree of replication was much lower. Unlike Study 1, Study 2 had no ambient treatment because our goal was to investigate the effects of predicted extremes of rainfall. First, let's summarize the results for groups that include both fungivores and predators. The width of the arrow will indicate effect size. There will be 3 arrows for Study 1, but only 2 for Study 2 because year 0 represented initial conditions. Mite densities increased twofold in Ben's experiment, were not sampled in Study 1, and were higher in the high rainfall treatment of Study 2. Adult and larval beetles increased in Ben Chen's study, and adults showed a similar but weaker response in Study 1. In Study 1, larval beetles showed a delayed response of 1 year, reflecting a generation lag. And in the rainfall manipulation, beetle densities did not respond to the treatment. Analyses of summaries of the remaining taxa require a more elaborate key because sometimes densities were near 0 in both treatments. So in interpreting the absence of a treatment effect can be problematic, and some responses of Study 1 were negative. In Ben's study, all Colembula families increased after 1 season of resource addition. Fall entomobryids showed a similar pattern in all 3 years of Study 1. Hypogastrurids in fall samples showed a similar response but delayed. And like thomysurids, onychurids in the fall showed an immediate positive response that lasted 2 years, but then they decreased in ambient and supplemented plots to near 0. Smiththerids in both seasons showed a strong delayed response that lasted just 1 year. Except for the delays, these patterns support the hypothesis of bottom-up control. But the thomysurids displayed a dramatically different response. Summer populations failed to respond the first 2 years, and then densities were lower, not higher, in the resource-supplemented plots. Isotomas in the summer showed an even stronger negative response. These 2 patterns are distinctly not bottom-up control. Manipulating rainfall had weaker effects, but when present, they were all in the same direction. In Ben's experiment, all predator densities had increased twofold after 1 field season. In Kendra's study, wandering spiders in all 3 years and in both seasons showed a similar response, though the effect size was smaller. In Study 1, spiders sampled by the Kempson showed no response, and centipedes were too rare to be tested. The other 2 predator categories exhibited unexpected patterns. The increased densities of web-spinning families in year 1 had completely disappeared by year 3, and pseudoscorpions showed a negative response to increased resource the final 2 years, the opposite of bottom-up control. In Study 2, the generally weak response by predators to differences in rainfall mirrors the varied and weak responses by several Colembula families. The positive response to high rainfall by cursorial spiders parallels the strong and consistent positive response by Thomiserid Colembula, a major prey of wandering spiders. Altering rates of detrital input and rainfall clearly altered community structure, with differences between treatments increasing over time. Fewer taxa displayed a significant treatment effect in Study 2, due probably to at least 2 factors. First, the rainfall manipulation was a less intense perturbation, especially with respect to enhancement of fungal growth. than the resource supplementation of Study 1. Secondly, Study 2 had a lower degree of replication and hence lower statistical power. Nevertheless, many taxa did respond positively to increased rainfall, with none showing lower densities in high rainfall treatment. Both fungivores and predators responded in Study 2. The occasional univariate interactions with site reveal the value of replicating experiments at different sites in the same landscape. Study 1 revealed the most surprising patterns. Some taxa on different trophic levels displayed a negative response to enhanced detrital input, either consistently or with a time delay. These patterns contrast sharply with a hypothesis of consistent and overwhelming bottom-up control. Some changing responses in Study 1 no doubt reflect variation between years. It's difficult, however, to invoke temporal variation as the major cause because several fungivores and predators initially showed a positive response in year 1 and negative responses only appeared in years 2 after detrital input had been increased fourfold. Shifting competitive relationships between Collembola and other fungivores and shifting patterns of intragill predation among the generalist predators are just two of many possible explanations for a pattern much more complex than simple bottom-up control of fungivore and predator trophic levels. Both studies strongly suggest that field experiments designed to gain insights into consequences of climate change on the structure of the leaf litter arthropod community must be continued for several years if one hopes to uncover new community equilibria. Thank you for your attention, and my colleague will answer any questions you might have.
Thank you very much, David. Any questions from the audience? Well, I have
Hi, Maria. Sorry, can I ask a question? Hi. Thank you for your presentation. I was wondering, in one of the last slides you showed different responses of various springtail families to the treatment. And I was wondering, can those responses be related to the function, to the ecological characteristics of the springtails, like whether they were more or less able to jump, like if they have developed furca and so on, these kind of things?
That's a good question. I think the spinthurids and hypogasturids have a history of heterogeneous distributions and population eruptions. I think what was surprising was the response, the negative response to resource of some of the larger bodied families like the tomocerids, which routinely showed a positive response to resource supplementation. But I confess ignorance on exactly what the different feeding habits of these families are, but I'm sure it reflects, some of that is reflected by differences in feeding specialization. I think, though, that part of the answer to part of the explanation for the differences is due to shifting competitive relationships and also shifting predation pressure, perhaps, by some of the generalist predators after their populations had increased after more than 1 year of manipulation. Because we've shown from other experiments that wandering spiders can have a strong impact on tomocerid populations by depressing them, but the effect only appears after a year of increased generalist predator buildup. So I think a lot of the answers have to do with time delays in predator-prey interactions in addition to competition.
Thank you.
Hi, I was really, I appreciated the way how you tried to avoid dispersal effects in your experiments, and I can see how difficult that is to do in the real world. But I was wondering, were you only fencing out the larger predators or everything?
We ignored vertebrates, of course. So we've done other experiments with vertebrates on the impact on the arthropods. We fenced the rainfall treatments because we wanted to model this as slice of the larger forest. We also had 4 unfenced and unroofed reference treatments in which we measured all the fauna and measured decomposition rates. So actually, an open and a fenced plot represents 2 different models. The open plots represent patches of differences in detrital input and moisture, and the fenced plot is more of a model of the larger system. But it was surprising, actually, that in study 1, that the interaction between the resource treatment and year showed very few interactions with fencing, even for the univariate variables. Fencing itself had a clear impact on some of the populations, as you would expect, but the interaction between the resource treatment over time and fencing was minor for most cases. So I don't know if that answers your question. Fencing or, well, that's it. We just wanted to prevent some of these larger mobile predators over 3 years from changing the results, and that's why we fenced them.
Yeah. Okay. Thank you.
Yes, of course.
You were speaking consistently about delay effect in the experiment 1
Yes.
year, but my understanding was that in the next year the doses was actually 4 times higher. So cannot that be doses effect rather than time loop
Right,
effect?
exactly. That's true. And the dose effect in years 2 and 3 were comparable to Ben's short-term experiment, but some of that is undoubtedly due to a dose effect.
Any more? Well, I would like to make a question probably on the behalf of many PhD students that have an experiment with so many replicates and they have to decide where to sample, where very intensively or keep the replicates for later. What would you recommend? Sample per seasons like you've been doing here, or keep the replicates and probably sample every year?
My suggestion is to hire lots of undergraduate assistants and sample as intensively as you could. We sampled less than 5% of the litter each time we sampled. So I think sampling more often would have been better, but we just didn't have the
Okay, thank you.
logistical help to do it.